This lecture is going to deal with bond dipoles and molecular polarity. So we'll start off considering the molecule hydrofluoric acid. So hopefully we should be able to draw a Lewis structure of this pretty quickly, and we end up with a hydrogen and fluorine with a single bond with 3 lone pairs of electrons around fluoride. And when we take hydrofluoric acid, for example, one of the interesting things about it is if you take this molecule and you put it into a device that could apply a magnetic field, so here we have 2 metal plates, and if you just put this molecule in, if we could look at it, the molecule would just be in some random arrangement, and you can see the hydrogen is the little blue piece, the fluoride is the green piece, and these molecules are just arranged in every direction. But if we were to apply a magnetic field to these plates so that we have a negative magnet and a positive magnet, one of the interesting things we see is all of these molecules actually line up in the same direction, where the hydrogen is pointing towards the negative end of the magnet and the fluoride is pointing towards the positive end of the magnet. And what we're seeing here is this is evidence that HF, hydrofluoric acid, while overall a neutral molecule, has a part of the molecule that has a partial negative charge near the fluorine and a partial positive charge near the hydrogen. And so another way of saying that is HF must be a polar molecule. It has regions that are positively charged and regions that are negatively charged. One way we can represent that as chemists is what's known as with a electrostatic map. So if you see these types of drawings or computations, what they're trying to illustrate is where you see the red color turns out to be a negatively charged area, where you see the blue color is a positively charged area, and where you see the green color is a neutral area. And so what we're seeing is there's a lot of electron density near the fluorine, turning it into a partial negative charge, and then that leaves a partial positive charge near the hydrogen. Again, evidence that this is a polar molecule. And this is really evidence that when we think about bonding, we've started off talking about a couple different types of bonds. We talked about an ionic bond, and this is a bond made through the attraction of a cation and an anion. So in this case, we have a full cation and a full anion, and this ionic bond is just nothing more than the force of attraction between a positive and a negative charge. We've discussed a covalent bond, where 2 electrons or more electrons are shared between nuclei. And so in this case, we have equal sharing. So these 2 electrons are equally associated with this carbon and equally associated with this carbon. And what we're now seeing is there's something called a polar covalent bond. And a polar covalent bond is really somewhere in between an ionic and a covalent bond. It's still a covalent bond, but it's not equally shared electrons. So these electrons are associated with one of these atoms more than the other. And in this case, they're closer to fluorine. And so if you imagine these 2 electrons being closer to fluorine, this starts looking more and more like fluoride, F-, and the hydrogen ends up looking more and more like H+. And so this polar covalent bond is an unequal sharing of electrons. One atom pulls more electrons towards itself, and this ends up with a partial negative charge and a partial positive charge. So when we do have these polar covalent bonds, we need to be able to sort of symbolize this and understand when they occur. So just a couple ways we can symbolize this. One way, which we've sort of already shown, if you see this, this is a delta symbol. And anytime you see this delta, what this means is partial. So it's not a full -1 charge of an anion, but it's a fractional negative charge. And here we have a fractional positive charge. We can also use these electrostatic maps. And again, red means negative, blue means positive. All right. And the other way that chemists illustrate this is what's known as a dipole arrow. So this arrow here is called a dipole arrow. And notice a couple features about it. It is an arrow. The head of the arrow points to the negative end of the molecule. So this is always going to go towards the negative end of a molecule. And then on the back end of the molecule, instead of just being an arrow, there's a little plus sign, right? And this plus sign symbolizes just that this is the positive end of the molecule. So the dipole arrow is showing the direction of the sort of dipole in it, that's showing the direction of the negative charge and the positive charge. So we can start to look at electrostatic maps of various molecules, and so we can go through a couple. And we won't spend too much time on this, but I just want to illustrate that when we talk about something being ionic or covalent or polar covalent, those are sort of clear-cut cases, and in reality, everything's a little blurred. So something like sodium chloride, we can think about being ionic, and we will for this course. In reality, it's sort of this combination. It's mostly ionic, but there's a little covalent character. Cl2 is a completely covalently bonded molecule, and then something like HCl is covalently bonded, but it's a polar covalent bond. All right, and one of the questions we have is, why is it that one atom is going to attract more electrons than the other? Why is it that chlorine pulls the electrons in HCl to it more than the hydrogen does? Or why does fluorine do that in our previous example? And the answer to that comes into another term, and this term is electronegativity. Electronegativity is the ability of an atom in a molecule to attract shared electrons towards itself. So this only occurs in covalently bonded molecules. And the greater an atom's electronegativity, the greater the ability to pull electrons towards itself. So it's this measure of, if you have a covalent bond, how strongly does one atom pull electrons towards itself? And we can start to think about this through our knowledge of the periodic table and ask ourselves, what elements are going to be really good at pulling electrons towards themselves? What are the elements that are going to be the most electronegative? And when we start to look at the periodic table, what we see is the closer you get to fluorine, the more electronegative, right? So our two periodic trends are, as you go left to right across the periodic table, electronegativity increases. As you go up a group on the periodic table, electronegativity increases. So why is this? Well, left to right, what we're seeing is an increase in Z effective, right? So +1, +2, +3, +4, +5, +6, +7. So the higher the Z effective, the greater the pull of the electrons. Why does electronegativity increase going up? Because size gets smaller. Fluorine is the smallest of the halogens. These all have approximately 0.7 Z effective, but fluorine is the smallest, meaning those electrons would be the closest to the fluorine nucleus, making it the most electronegative of the atoms. Right. Now, also on this periodic table that I'm showing you, you see these little values below all of the atoms. So boron is 2, carbon's 2.5, nitrogen's 3, oxygen 3.5. So those values are what we call electronegativity values. And these were developed by Linus Pauling, and it was a way of sort of classifying bonds. And so what Linus Pauling said, and the system we still more or less use, is if you compare the electronegativity values between two atoms that are bonded together, and you take a difference between those two, right? If there's no difference between those two, then it's a covalent bond. If there's a little bit of difference between those two, it is a polar covalent bond. And if those electronegativities are really, really different, we call it an ionic bond, right? Where in this case, they're so far different, we've had a full transfer of electrons. Now, to put some numbers to it, what Pauling said is this no difference in electronegativity values is really a difference of less than 0.4. The intermediate case of a polar covalent is if the electronegativity difference is between 0.4 and 1.8. And then lastly, this ionic compounds are values greater than 1.8. And so from these, we can start to look at different bonds and identify what type of bond something will be, right? And so, for example, we can look at something like sodium chloride. And what we would do in this is we'd say, okay, sodium is 0.9, chloride is 3, so 3 minus 0.9 is going to be 2.1, and 2.1 is going to put us right in the ionic range. And so we'd predict that sodium chloride is an ionically bonded compound, which is hopefully what we already sort of came up with. Then we can look at HF. And if we look at HF, again, we'll take fluorine 4, hydrogen 2.1. And so here we have a case where we end up with a value of 1.9. And this is sort of a tricky one because 1.9 we see is really kind of down here. But most people, while your book lists this as according to this, an ionic bond, most of the time you see this value as a polar covalent bond. So this 1.8, I would actually call this above a 2 is ionic. But again, this gets at this sort of things are not as cut and dry as we may hope them to be. There's gray areas here. And then we have our CH bond, and our CH bond is going to be a non-covalent bond, right? And so, and I would say this pure covalent is less than or equal to 0.4. So I wanted to show you this table to show that it's probably best if we modify this table and say this is less than or equal to 0.4, and then this is between 0.4 and 1.8, and this is greater than 2 for our differences. One of the key takeaways here is the carbon-hydrogen bond is a non-polar bond. So anytime we see carbon-hydrogen, we can think non-polar. Now, water is a polar molecule, meaning it has a dipole moment. And so when we think about the Lewis structure of water, right, we can see that there's 2 bond dipoles. This oxygen is more electronegative than hydrogen, so oxygen is pulling electron density towards it. Oxygen is pulling electron density towards it. And so we have 2 bond dipoles. And often what we think about then is coming up with an overall molecular dipole, shown here. Here's our molecular dipole. And this dipole arrow is really nothing more than the sum of these 2. So you can think about sort of adding these 2 arrows together to get the overall molecular dipole that we see in this bottom picture. And that's important because when you think about what's going to make something polar, you have to understand what the shape of the molecule is. You have to understand what bonds will be polar, and then we have to figure out what is the overall polarity. Now, let me give you another example of this. We can ask ourselves, is carbon dioxide polar? And as we look at this, we could look up electronegativity values, and we'd say, well, the oxygen carbon bond is a polar bond, pointed away from carbon towards the oxygen. But if this oxygen is pulling hard to the right, and this oxygen is pulling hard to the left, the pull of these oxygens effectively cancels each other out. And we say CO2 is nonpolar. It has polar bonds, but because they pull in opposite directions, CO2 is going to be an overall non-polar molecule. And what this means is when we talk about the polarity of a molecule, this is going to depend on both the presence of polar bonds, but also the molecular structure. And so if you want to determine if a molecule is polar, you have to first draw the Lewis structure. You have to determine the molecular geometry. You then have to determine if there's a bond dipole, and then you have to determine, do the bond dipoles cancel each other out or not? And at that point, you can answer the question, is that molecule polar? So I encourage you now to go on to the worksheet on this material and watch the video on that for the answers to see some problems related to this topic. Thank you.